Good morning, everybody. Once again to the JKMRC Friday Seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners of this land, the Turrbal and Jagera people. Thanks, Dion. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connection with country, and we recognise their valuable contributions to Australian and global society. Our speaker this morning is Dr. Janelle Simpson, Principal Geophysicist at the Geological Survey of Queensland. GSQ has in recent years conducted some truly remarkable regional geophysical surveys, collecting foundational data such as deep crustal seismic profiles and magnetotellurics over this state's world-class metallogenic provinces. Janelle has been instrumental in driving these acquisition programs and producing products that forward-thinking, early-moving exploration companies can and have used in their ground selection strategies. Today, Janelle will be presenting the results of recent MT surveys the GSQ has conducted over the Mount Isa province and talking about how those results can be integrated with other data sets to better understand geological questions, both large and small. Her presentation today is titled, Using MT to Understand the Mount Isa Province. Please join with me in welcoming Dr. Janelle Simpson.
Yeah, and hopefully this works. It does, great. I need to hire Tom to do my bios. That was wonderful, thank you. So I work with the Geological Survey of Queensland. I've been there for quite a while. For my background, I'm a geologist by training first, and then I've gone into geophysics throughout my career. So I've got a PhD in magneto-tellurics from Adelaide Uni, and I've been working with MT for, I don't know, since 2014, 2015, about that amount of time. And during that period, we've done a lot in Queensland. So I'll take you through what we do with all this data that we collect. Before I start, I'll also pay my respects to the traditional custodians of the land that we're meeting on today, the Turrbal and Jagera people. But also I wanted to draw people's attention to the fact that for anyone who's unaware, Queensland is on a path to treaty. So the Queensland government has committed to generating a treaty with our First Nations people, and there's a whole website around this, and this pledge is on the website. And I think this is a wonderful thing for people to go and read. The bit that I particularly like is that Queensland, we will commit to be courageous, curious and optimistic as we hear our First Nation people's stories. So I think we can all engage with this path to treaty process. The work that I'm doing is the collective effort of a lot of different people. So I'll be presenting 3 different studies using magneto-telluric data, one done with Karen Connors and Dominic Brown, one done with 2 co-authors down at Geoscience Australia, and the third one, the depth to basement study, is done with Hoel Salil from CSIRO. So it really is a collaborative space that I'm working in here. The data has been funded either through Queensland government or the federal government. My geophysical contractors never get any mention, but they're out there collecting the data for me, so I don't have to dig a million holes and bury equipment. So they're a great help to us. And then there's a heap of the community involved in this as well. So there's free codes, there's free plotting tools, all made available by the MT community. So it really is a big collaborative effort to get this sort of stuff done. So for anyone who is not familiar with the Mount Isa province, we sit up here in the north of Australia, and we are actually on the broad eastern margin of the North Australian Craton. So the North Australian Craton occupies the top third of Australia. It's a Proterozoic to Archean Craton, but I'm only really interested in the Mount Isa province. So we've got exposed Proterozoic rocks here in the brown, and then around that we've got Phanerozoic cover basins. So that's concealing these older rocks that we're really interested in. And as Tom mentioned, this is a world-class minerals province. There's all sorts of different mineralisation styles here, and it's been a huge focus for us in government for a long time, and it's been a huge focus for the exploration industry as well. If I zoom into this yellow box to give you a bit better feel of what's going on, this is probably not as clear to anyone else as it is to me. This is how my brain works about what's going on. So the blue and pink and green colours are the outcropping extents of the Mount Isa province. There's 3 broad subdivisions up here. We've got the Western Fold Belt or Western Sub-Province, depending on who you talk to, the Eastern Sub-Province, and then sandwiched in between, we've got the Chalcodon Leichhardt Belt. And all of these black points are MT sites that have been collected over the years. So you can see there's a combination of transects, often along deep crustal seismic lines, but also big arrays of data like this one here down around Boulia, and this one here up around Cloncurry. So Cloncurry is here for reference. Mount Isa sits in here, and Boulia, it's down there, that's Winton. So we're really in quite a large area of Western Queensland. Trying to summarise what is a very, very complex terrain in a slide. I have pre-1850 Proterozoic basement in Mount Isa. So that sits underneath what is essentially 3 stacked superbasins. So the oldest one is the Leichhardt superbasin. Sitting on top of that at about 1700 is the Calvert superbasin. There's a slight gap in deposition, and then the Isa superbasin sits on the top of that. So these are not normal basins, these are super basins, these are enormous packages of rocks. And a lot of the lead zinc mineralisation is actually associated with the youngest of these super basins. And then you take all of this and then you cram it through an orogenic event. So this is a complex multi-phase orogenesis that deformed all these rocks. There's faults, folds, everything you can think of that has been done to a rock has been done to these rocks. And then on top of that, you put a bunch of younger cover basins so you can't see them anymore. And then you try and understand them. So that's kind of what we're dealing with here. If you plot up where we find minerals in Mount Isa, all these black points are mineral occurrences. And then you plot up where the rocks stick out of the ground, which is this black hashed area. That's where we find things, where we can look at the rocks. Where we can't look at the rocks anymore, we don't find them. We have, so this is a depth to basement map. So you can see these white or pale colours are quite shallow. So these are only, a couple 100 metres down. We haven't buried them very far. We can still drill into them. We can still mine out of them. We just can't see them anymore. And then we don't find things as easily there. And so it's more expensive. You can't see the rocks. It's really hard to ground truth any interpretations you do. So geophysics is usually used here, but can't ground truth that either. So you just do the best you can. And we haven't been hugely successful. There has been some success stories, but we can obviously do better here, because if there's that much mineral endowment sticking out of the ground, there's no reason to think it would stop simply because you can't see it anymore. So geophysics, obviously the best tool of all time, not that I am biased, but there is a really big problem. So in the electrical geophysics space in Mount Isa, there's a really big challenge. So most of our conventional exploration uses airborne EM or a ground-based EM that's generally looks down, 100, 200, 500 metres, looking for where things are drillable. In Mount Isa, we have this wonderful basin called the Carpentaria and Eromanga basins, which are full of a very, very conductive shale, which means that instead of being able to see a couple 100 metres down, we can see like 25, maybe 50 on a really good day. You can't see through this with conventional EM techniques. And so if you go on the ground and pump huge amounts of energy into the ground with a ground-based EM system, you can get some penetration, but it's really difficult. It is really, really difficult. So MT is the tool that we're using in the electrical space to try and overcome this. It's not just challenges, there are opportunities in Mount Isa in the geophysics space. So it's obviously been very well explored for a long time. So there's huge amounts of historic data. There's every kind of geophysics that you can imagine. There's geochemistry, there's geochronology, there's drilling. There's a lot of things here that you can try and pull together to understand what's going on. And a very active exploration community as well that allows you to talk to people on the ground and see what they're up to, see what their challenges are, see what sorts of information they actually are interested in learning. So if I pause a second and show you what the deep electrical structure of Mount Isa is. So this is based on a data set collected at Geoscience Australia. These triangles are magnetotelluric data, but they're long period magnetotelluric data. So instead of seeing, the top, 10, 15 kilometres, you see from about 25 kilometres down to over depending on the data, but somewhere in the realms of 100, 200 kilometres down. So it really is really big scale electrical imaging of the Australian continent. And they're collecting them at 55 Ks. They're trying to get it across the whole of the country. We're working with them on this. But this is the model for Mount Isa. You can see there's a really striking electrical structure in Mount Isa. This is the Northern Territory. Obviously, they don't have as much cool stuff going on as we do. So in Mount Isa, we've got this really, really strong crustal conductor that's running down the eastern side of Mount Isa. So this is one of the strongest conductors on the Australian plate that we know of so far. It's called the Carpentier conductivity anomaly. And then right next to that, we've got a very strong resistor. This resistive block actually extends down into the mantle. So it is quite an impressive feature. And then down the western side of Mount Isa, we've got another moderately conductive feature. So you kind of got this big block of resistivity in the middle and two conductive structures wrapped on either side. And this is really, really important because there's been this case study done in South Australia where, and this is not the only one, this is just the most famous one, so I put it on my slides. So Graham Heinsohn down at Adelaide Uni conducted magnetotelluric studies over the Olympic Dam iron oxide copper gold deposit and found that there's a really strong linkage between these big mid to lower crustal conductors and where we find iron oxide copper gold deposits. So there seems to be some sort of linkage from Olympic Dam through a finger-like conductor into this mid-crustal conductive source. So this is obviously very, very exciting if you're looking to try and find a mine like Olympic Dam. And if you go to Ernest Henry, which is a mine like Olympic Dam, it actually sits right on top of this part of the conductor. So it's a very, very similar system. They're very similar aged rocks. And we seem to have a situation here where we can use MT to understand where these big deposits might be. It probably hasn't been done enough to know how reliable this correlation is, but it looks pretty good based on everything I've seen. So that's the best knowledge we've got so far. So do a bunch of MT, done, sorted. We'll find every deposit and we'll just run MT forever. Easy. So we have been running a hell of a lot of MT in Queensland. When I started at the GSQ, we had, I think, 320, 330 odd sites. We now have over 3,000. So we really have had a big focus on acquiring this data. Most of these sites live in these big arrays. So this one here up in Cloncurry is about 1,000 sites. This one here is 1,600 sites. And then there's a whole heap of these profiles as well. The blue sites on this map are points that I am collecting starting 2 weeks from now. So that's our next phase of surveys. And as I go through the talk, I'll show you why this survey looks like this, because it's kind of ugly, and what the thinking behind that survey is. So in the big scale picture, in the AusLAMP space, this is the work done with Geoscience Australia. This is what we've managed to collect at the moment. It's a little bit outdated. We've got a few more in here, but we've gone through and prioritised the rest of the sites in Queensland, and we're going to try and move down the east coast, understanding that part of the state, and then move into the Cape and into central Queensland. These sorts of lower priority areas for mineral exploration. So hopefully, over the next 5 years, we can have a lot of data coming out in that space. So I'll give you 3 different case studies today. So this is all the work I've been doing. This is the ones I'm going to actually talk about. So there's a big focus from a couple of years ago was a deep crustal seismic interpretation project. So we have a huge amount of deep crustal seismic data across Mount Isa. So there's this network of white lines are all deep crustal seismic. And there was never a cohesive interpretation. It's been collected between like 2007 and 2014, 15. And then once you collect it all, you go, oh, well, that was really hard work. And there's like isolated interpretations done after each survey, but there's never been an effort to put a cohesive interpretation together. So we got together with Karen Connors and ran through that process. I'll talk about that project. I also wanted to show you that it doesn't just have to be the really big scale stuff. We're doing a depth to basement study with CSIRO, trying to understand how can we best use MT to image where the basement is so that we can de-risk drilling for our mineral explorers? And then this bit of work down here, inverting data from the CF23 survey and the Cloncurry survey. So that's these two lines of data down here is CF23, and that's the Cloncurry data set. How do we use that deep crustal seismic interpretation to hang those interpretations on and make better sense of them? Oof, I'm going to have to keep going. All right, so the deep crustal seismic project. So these are the major structures that came out of the deep crustal seismic project. So it's kind of not quite genuine to put those up at the start of the project. But anyway, these are all the lines that we reinterpreted. We didn't venture up onto this set of lines in the first phase of the project. We did that in the second phase of the project. That report is stuck in publishing hell, so it will come out as soon as we can get it through there. But the first phase of the project looked at all of these deep crustal seismic lines, trying to get a cohesive interpretation, work out what the big structures are, what the big crustal blocks are, and what that means to how you understand how this terrain was put together, how you understand where fluids might move through these terrains and cause mineralization. So it was a combination of seismic interpretation. We did some gravity modelling as well, and some geochronology, as well as the MT. So it really is a big multidisciplinary study. And this was the outcome. This is looking from this purple arrow down here from the bottom of the Mount Isa province, the Cork Fault, up across this entire network of seismic lines. And these are down to about 60 kilometres. And you can see we've got cohesive blocks of mid to lower crustal material that are distinctly different from adjacent blocks. So these have been interpreted from the seismic, checked with the gravity, and it's probably not true, but it's the best that we've got. This is the best truth that we've got so far. I'm sure it's wrong in detail, but it gives at least a cohesive framework that you can start to try and understand the rest of what's going on top of it. There is a report. If you want to read about what we've done in exhaustive detail, you can go and read a very long report. It has a lot of pictures. I promise you it's not terrible, but it is very long. So then so these major structures, they form the boundaries between some of these big crustal blocks, right? And then you take that and you overlay it on the mid-crustal conductivity structure, and you see that, oh, well, maybe this conductive feature that we are very interested in associated with the Ernest Henry deposit has some sort of relationship to this big structure called the Gidger structure. So this is potentially terrain boundary. This could be, some people call it a suture, some people debate whether it's a suture. There's a lot of strong feelings about it, so we have called it the structure, and we are being a little bit agnostic about exactly the timing of movement or closure or anything on the structure. But there does seem to be a very strong relationship between this crustal conductor and the Gidger structure. But our data stops here, unfortunately. So the data that this model is based on stops up here. We went and collected this data set here along the CF23 seismic lines. And so we're like, oh, well, why don't we model this data and see if we can see something here along the Gidger structure similar to what we're seeing further north. That's a sensible sort of hypothesis to test. And this is what happens when you do it. So what I've done is I have taken deep crustal seismic. This is the line work from the interpretation we did with Karen. And I've stepped through every single deep crustal seismic line that crosses this structure to see if I can find some sort of cohesive magnetotelluric signature. So I've taken the seismic, I've got a structural interpret on top of that, and then I've put a magnetotelluric model in transparency on top of that. So I'm really stacking geological understanding, seismic data, and magnetotelluric data into the same space. Was I clever enough? No, I was not clever enough. I was going to, so this here is the Gidger structure so I'm moving north to south. So this is the seismic line IG1. That's the Gidger structure. And here it's like this big tabular body that separates this piece across, which is quite different to Mount Isa here on the left. So you can see there's something conductive going on inside the structure. This model doesn't have a lot of resolution down here, but I would expect that this is quite conductive under here. As you step next one further south, this is quite a different angle to be looking at this. So you get a kind of strange squashed gidger structure coming in through here, and then a big conductive block that sits right on the location of that structure. Next one further south, this one is straight across the bottom of the outcropping extent of Mount Isa. This is M6. The gidger structure down here has this weird kink in it as it interacts with the Cloncurry Fault, which is a very significant structure that runs down through here. So it's got this weird kink in it. You've kind of lost this really strong conductor, and it's not quite clear what's going on here. So you've got the same structure in the seismic. It's similar in nature. So you've got this conductive thing under the gidger structure and then some conductive things that come up off it in the hanging wall, very similar to what's going on up here, but it's a lot less intense. And so we have quite a gap in data here. So we're not quite sure, does the intensity of that structure decrease as we move further south, or are you looking at something a bit different? It's hard without the intervening data to know. And then as you step down here, this is the lowest resolution data that I have. This is 10K station spacing. And you can see the effect that that lower resolution data has on the quality of the structures you can model. So this is the gidger structure here, this weird kinked thing again. There's obviously a significant change from conductive, more conductive crust to the west of that structure to more resistive crust with bits and pieces going on inside it to the east. So this is Mount Isa in here. This is the normal terrain, which sits outboard of Mount Isa. And then you've got the suggestion that something similar to this is going on. It's not like you have to have looked at a number of models. I'm only showing you one. So you'd have to take some trust in what I'm telling you, unfortunately. But you've got a similar thing where you've got conductive structures associated with heavily faulted things coming up in the hanging wall from this mid-crustal conductor. So that's the story that you can tell yourself if you combine the seismic data, the geological understanding generated from that and the MT. But it's not that satisfying because we have big gaps in this data set. So we're not exactly sure how to interpolate between the various models we have. But this is a beautiful model put together with Karen. This is using existing modelling. This is not our modelling, it's published modelling. And if you put our structures over the top, you can come up with a story about where you're getting fluids flowing through the crust and potentially interesting targets for exploration. Obviously, no one is drilling this deep, so this is 60 Ks, so this is no one's drilling down 30 Ks to find out what this is, but maybe you've got something in more shallower areas that you can actually reach and find out what's going on.
Sorry,
yeah.
Just had I can't see the pointer in
the. Ooh.
So, mouse.
Which mouse? All right. Well, I'm going to stand over here and wave a mouse around and a pointer as well. All right. Ready for this? Okay. So apologies, everyone online. That was a lot of waving a pointer around. I'm not going to go back and do it again, though, or I won't finish the talk. Okay, so the upshot of this whole story about using this seismic data to try and understand what's going on and then using the MT on top of that to get a better picture is that we end up with a feeling that this structure probably does continue to the south. The CCA is probably present in the southern part of the Mount Isa province, but it looks like it could be of lower intensity. So it would be really nice to understand where that happens and come up with some sort of idea of why that might be happening and what the implications are for mineral exploration. Maybe you need that really strong crustal conductor to feed these systems, or maybe it's not. Maybe a moderate conductor is enough, right? This resistive block that is in the middle of Mount Isa does seem to continue down to the south. It's quite strongly present in this big array of data that I haven't shown, but it continues all the way. And interestingly, that resistive structure, there's nothing conductive anywhere on this MT line. It was the saddest, most disappointing MT I've ever collected. It's like resistive all the way through the crust. There's a really conductive basin on top, and then to at least 50 Ks down, there is nothing. just resistive crust. So it's interesting that this structure here doesn't seem to have any electrical response. And if you go over here, it's not that compelling either, right? So there's an interesting story down here, not the point of today. And then this western conductor, we pick up on the western end of this profile and down in this array as well. So it looks like the structure that we're seeing in the north has quite a good continuity in the south, but we didn't previously. Like, you could guess that was going to be the case. Everything's that way in Mount Isa, but you're not sure unless you check. So that's checking that story is what the CCA-MT survey is about. This is the forward-coming survey that we've got. So it's kind of like a horrible beast of a survey in 3 parts. There's 3 things I'm doing. This high-density line up here is to be collected along previously collected deep crustal seismic. So there's a seismic line that runs straight through the guts of Mount Isa. It doesn't have any MT on it. It would be lovely to be able to do this same thing on that seismic line. So collect slightly higher density data there. This big set of lines through eastern Mount Isa is really about tracking from the Cloncurry survey in the north down to the south in explorable areas where that mid-crustal conductor is going. Where is it? Are we actually sure it's associated with the Gidja structure? And then if we are, where does it change in intensity? Is it gradual? Is it sharp? And then I attacked 3 lines on the bottom because it's really important to know if this crustal conductor stops where Mount Isa stops, and it might not. There's some indication that this conductor might continue off the end of Mount Isa. This is a very, very serious time gap. This break in the magnetics is a huge time gap. So if it continues off the end of that, there's really strong implications about what is actually causing this, and it can't just be a Proterozoic sourced structure anymore. It has to be understood a different way. So I'll start getting data like in a couple of weeks, and then I won't have an answer for a couple of years because that's how modelling works. All right. So that's the biggest picture study that I've been involved in. This is the most detailed study that I've been involved in. So I'm trying to show you the versatility of this data set, or this kind of data. So we have zoomed right into the Cloncurry area. Cloncurry, this time I've actually labelled on a map, is here. Quamby has a newly opened refurbished pub with a pool. So if ever you're up here, go to the Quamby pub. I have not been there yet, but I'm hoping to go. And then the Ernest Henry iron oxide copper gold deposit sits at this enormous star, so you can't miss it. So we're in an area that is very, very prospective. But also quite shallowly covered, right? So these colours, anything that is not white is less than 100 metres down. Right? It's not very far to go to find the rocks that you want to mine. And it's adjacent to a very significant mine. So we thought we would use this data set and see if we can better define the depth to basement for this project area. And we're sitting right on top of the Gidja structure. So the Gidja structure is a west dipping structure that sits underneath this. So we're right on a terrain boundary, very interesting for mineral exploration. Shallow, perfect area to go and do a bunch of studies to try and help mineral exploration. So this workflow has been developed by Hoel, so I'm not trying to take credit for it. I think it's a wonderful workflow. So it's 2 stages of probabilistic modelling, and I love some probabilistic modelling, so it's right in something I want. So what you're looking at is you take an MT site, a single MT site, and you run a probabilistic model. So this model is telling you this is depth on this axis and this is resistivity. So you've got something quite resistive right in the near surface. This is probably an artifact because the data is not sensitive to something that shallow. You've got a couple of conductive layers that sit in here. This is my basin. And then you've got this broad spread of probabilities that's associated with the basement depth. So this is a very typical result you get out of trying to find basement with MT. MT is not sensitive to the top of a resistor, and basement is the top of a resistor. And so we have a limitation here. And so what we do, rather than say, oh, well, MT is no good at that, you do a probabilistic inversion and say, oh, well, MT said it's like between there and there. And then you try and combine it with other things to make that prediction more accurate. So if you just use the MT, you can see the probabilities have been filtered in this panel here to give you a probability estimate of where basement is, and that's just a coloured version of the same thing. And then you do it at every site. You do it at every site and you get a weird spread of different probability estimates of where basement might be. Just from the MT, so just from the MT at this point. And then what you do, because you have not had enough probabilistic modelling in your life, you take this probability from MT and you combine it with other data, and then you fit a surface through it using Bayesian inference. So that's what's going on here. So the MT says basement is probably there, might be there. The drilling says it's right there. This MT site's giving you a bimodal one again. That MT is giving you a different bimodal. And that drill hole says the basement is somewhere in here. And then you try and fit the best surface you can through this. So you don't just grid it. You do a number of different surface calculations to try and fit the best surface you can through all the data points that you have. And then you end up with a second probability distribution because everybody loves that. I've talked through all of this on one slide, but this is the result. So this is what you end up with. So this is just from half the data set. We have done this on all of the data set now. So I've got a north-south section. So south is on this side where you've got outcrop, and then this black wiggly surface with varying levels of fuzziness is our best estimate of depth to basement. You can see we've offset this by known faults so that we allow this model to incorporate offsets on faults to make more sensible geological models. And these red lines, the red lines that you can see in here are our drilling constraints. So it doesn't have to absolutely honour the drilling constraints. We put a bit of rubberiness on that because sometimes drilling picks are not quite right, but it honours most of it, as you can see. And so you end up with this kind of surface, and it's very useful to give people an understanding of how uncertain we are about the basement in this area. So for my mind, a surface like this that includes an estimate of uncertainty is a much more useful tool than a beautiful surface that is the absolute truth, I promise, which is usually what you get in a depth to basement space. So that's a very shallowly focused, for me, project. And then with that same data set, so exactly the same data set, the Cloncurry Inversion project is something we undertook. So this is taking the entire data set, and this is a more typical way of using this data. You just take the whole data set and you run a bunch of inversions, and then you find out what it tells you. Trying to understand as a first pass what the electrical structure here is. So as I mentioned, this is about 1,000 sites. They're on a 2x2K grid. All this data is publicly available. So if you want to do some modelling and tell me that my models are rubbish, you can do that, and I would love you to. So this is the context we sit in, as I've gone over a couple of times. We sit in the hanging wall to the Gidger structure here in the eastern succession of Mount Isa. We've got this conductive structure in the mid-crust that absolutely does extend into the deeper crust. This is just a bad model. So we're really focused in this area up here. This is modelling that was done in 2016. So these 1,000 sites of MT collected in 2 phases. After the first phase in 2016, we did some modelling with some people at Geoscience Australia. So this is Li Jing Wang and Jingming Juan is the other author on this paper. And you can see, so what I've done is I've taken a series of slices, horizontal slices through the model, stepping from shallow on the left through to deeper in the right. So this data set really only sees down to about 20 Ks with any reliability. And that's because there's something super conductive in the mid-crust. We can't see through it. As we collect longer period data around it, we can see deeper, but this survey only goes down to 20 Ks. But what we get is we get a very strong conductor down the eastern side of this array, and it's present at all levels, straight down into the mid-crust. And then there's this big resistive block that sits on the top, and punching straight up through this are some conductive structures. And if you put an isosurface on them, they get a lot more exciting. And then you put the mines on them and they get even more exciting. So you've got this conductive pipe-like structure. So we're looking from the south. So this is the array here. We're looking from the south here across the location of Ernest Henry. E1 is another deposit here. So there seems to be some sort of association, just the same as we see in in Olympic Dam, between these crustal conductors and these iron oxide copper gold deposits. But this is work that's been released in the public domain for a long time, so this is not new. The modelling that I've done on all of the data is relatively new. I have not given you a link to the report. Hopefully I have later in this slideshow. So this is not a trivial sort of data set to model. By the time you've got 1,000 sites of MT over this sort of area, it takes about 6 or 7 days for every model to run. And you can't just run one, you have to run, I run 16, but like it's a lot of compute power, and this modeling is done on a supercomputer, it's not done on a desktop. So you add all that together, it takes a long time to generate a series of models like this. So this is this is actually a progress model. This was part of the way through an inversion. You can see my RMS is still quite high. The red areas mean the model is not doing a very good job of fitting the data. So this is happening down here, which is not somewhere I'm that concerned about because we've modeled that previously. So I'm not concerned about that. There's a big set of, online people, there's a big set of misfit here in the middle of the array, which I am a lot more concerned about because these structures in here are starting to look very interesting and very similar to the ones we're seeing down around Ernest Henry. And then there's a big set of misfit along here. This is actually along a fault. You can see it's got a very linear nature about it. And what's going on here is I simply cannot. So I'm balancing model mesh coarseness so I can run my models faster and resolution so I can image these structures. I can't have the best mesh in the world to image all these structures properly. So what's going on here is there's a fault. There's obviously some sharp discontinuity in the electrical structure and I can't model it adequately with the mesh that I've got. So this is there in every single model. So it's a mesh problem. Let's see, what have I got here? So if you keep running that inversion, the RMS does get better, I promise you. It doesn't get quite as well as, like, it's good enough. It's a good enough match for the data that we've got here. So this was a model. So I think that's at about a 5Ks depth slice on that one. So the faults that you can see in that map view were not interpreted from the MT. They are structurally interpreted from magnetic data primarily. So you can see there's an amazing correlation there between the electrical structures that we're seeing in the MT and the faults that are actually breaking up this geology. So it's a very good first check of the sorts of reliability of this model. And then if you plot the potential location of the gigastructure, this is a bit dicey. I need to go back to my geologist about why that goes up. But most of them are quite flat in the mid-crust because we're taking a slightly oblique slice of the gigastructure here. You can see that we've got this very, very strong mid-crustal conductor that sits underneath the gigastructure, and then these bodies that come up off it. Some of them are not connected. So this one here is probably a near-surface graphitic shale body, but this one here is definitely connected down into the larger structure. So C5 is this one here. It's like a long kinked conductive anomaly that comes up into the near surface. And then if you compare this to what we're seeing in other parts, so stepping back to this understanding of using our interpretation of the gigastructure to understand different bits of MT data across the province. This is straight out of the Cloncurry model in the north here. So you can see conductive mid-crustal structure with bodies coming up off that. This is the one that I've been through on M6, and this is the one further south along CF3. So you can see we're getting quite a consistent story here. It's quite an exciting story for me, but it's kind of the focus of what we're doing. And again, it all feeds into this survey. So this is the kind of big scale program that we're using MT in. And then as we do more MT, we realize what the questions we need to answer are. And then we go through and plan more MT, trying to build up a framework of understanding in the electrical space so that we can help people choose tenure, essentially, is what we're up to. Unfortunately, this says it's going to be released in mid this year, but I haven't started it yet because it rained a lot. So end of the year, I'll give you some data. I think that's it. I think that's what I've been up to.
Janelle, that's fantastic. We'll just open the floor up for questions. Anyone?
2 from Steve. 3 from Steve.
I'm not allowed 3 though, am I?
Depends if anyone else fights you for the microphone, doesn't it?
Yeah. I'll go for the bigger one that's probably going to be of interest to the whole community. ISA region is wonderfully prospective. MT is very useful for helping us with prospect definition and a number of questions as you've highlighted. But your focus is all on at the moment, the work program is all on the southern end of the district. Mm-hmm. There's a lot of industry interest in exploring the northern end. So could you tell us your work program plans for that?
Yeah, so it's a good point, and the interest up in the north is more recent, and the lead times on these projects is very long. So I've been working on the CCA MT survey for like 3 years. There's a lot of engagement involved in trying to get these MT programs off the ground, so it's not a trivial thing. So when we planned this survey, this was where the interest was. It's certainly where our interest lies in answering this question, but it's absolutely right that the structure should continue north, and the conductive structure does look quite strong in the north as well. It all seems a bit deeper up there from my understanding. I've not done as much work, but there are shallow pockets that are potentially explorable. So I would love to expand this survey up to the north. I don't have any money at the moment to do such a thing, but we always have new funding packages come through. So that's absolutely something we'll be looking at in the next funding package we get, whether or not we have the staff and the resources to actually plan one of these big surveys and execute it properly.
I've got a question. Thanks, Janelle. That was very good. I appreciate geophysics a lot more. You made it sound very accessible. However, my question will show how shockingly little I know about geology of Queensland. I'm blushing, actually. You mentioned a couple of times sort of the word weird kinks. And even in your last couple of slides, it just looks like the structures are indeed kinking.
Yeah.
Any comments on that? Like, what would be creating the kinks? Like, what are your thoughts on that?
Yeah,
and like,
so that's
kinks are not normal.
No, they're absolutely not normal. And so what's going on there is the Gidja structure is quite old. It's really a very foundational structure in Mount Isa as far as we can work out. And then as you get subsequent deformation on top of that, it reworks that older structure. And so if you come and whack an enormous fault through it, it'll get offset and deformed in that subsequent activity. So it's part of the nature of these old, long-lived structures that they don't look the way you want them to understand exactly what the hell they were.
And it's not necessarily another structure?
It is another structure. Yeah, another structure is what's causing those deformations. Yeah. Sorry.
I'll just remind the folks online as well, if you wish to ask a question, please just raise your hand through the Zoom link or type it into the Q&A box. Thanks.
Hello, Janelle.
Hey.
Thanks, because I'm an MT fan, so this kind of presentations I like quite enjoyable, and also because of the potential of this method here in Australia. In Europe, it's a complicated method because of the cultural noise.
Yeah.
So here you are so lucky, and I think that it has like a great potential. So just 2 small questions. First, which is the role of faults in the probabilistic depth to basin modeling?
Okay, yeah.
So do you consider it
Yeah, so the role of the faults in the probabilistic modelling is essentially a surface at which there's no smoothness constraint applied across it. So if you've got a fault here and your surface, generally the surface has to be a smoothly varying surface, but as you hit the fault, you allow it the possibility of having an offset. You don't dictate that it has to have an offset. You let the data find its natural path by allowing offsets.
So you can consider it as a method also to locate faults.
Yeah, so we've fed in known faults. So the faults are usually interpreted from the magnetic data. Some of them are very clearly basement faults that have also been given to this depth to basement interpretation, which implies that they're being reactivated if there is an offset along them. But yeah, we're not interpreting new faults. We can't let it. We don't have a way of letting it do that. If it doesn't fit in some areas, maybe there's a fault missing, right? But we don't have a way of being like, put a fault wherever you want.
Yeah, and the other thing is like
let it do.
about the cytospacing. I think it's a quite difficult thing to decide when you do this kind of exploration. So are you happy with your cytospacing?
Yeah, so...
Or do you think it's quite coarse? And maybe in the Queensland new project, it's quite too separated for mining exploration, maybe.
Yep, absolutely. So my site spacing is usually dictated by the question I'm trying to answer and the money that I have. Those are my two constraints. And usually if I find that my federal colleagues are yelling at me for putting the sites too close together and exploration companies are yelling at me for the sites being too far apart, that's about my sweet spot. Right? I'm not trying to give people drilling targets. I'm not trying to run an exploration program for a company. So 2Ks is about as close as I would ever go personally. I have done 500 metre spacing in the south. That was the first survey I was involved in. Probably wouldn't do that again unless I had a very, very good reason for it. I will go closer together. So the new program, that's 10K station spacing. It's 20Ks between lines. Honestly, it's a little bit coarse, even for the questions I'm trying to answer. But I don't know where to put that higher resolution survey yet. So I have to do the coarser one and then I can go back and infill it.
Okay, and just really fast. When you have 2D, when you show 2D sections, empty sections, they are created with 2D inversions?
No, they're 3D inversions. Okay. So it's all 3D inversions because the data requires 3D inversion.
We have an online question that we'll go to now from Jim Morrison, and I'm asking this one very specifically because it's exactly what I was expecting to ask as well. But do you know what mineralogy is causing the deep conductivity? Sulfides, graphite, moisture?
I would not be a talk if I did not get that question asked. In this area, the best guess we've got is some conductive material that's been, and this word has all sorts of geological implications, entrained in the gidger structure. So we think there's graphitic shales that have been deposited in the paleoprote that have probably been subducted down into the gidger structure. Obviously, I believe it's a suture at some point. I've just given away my cards. But so graphite is generally the answer in the Mount Isa region. It is a very, very strong conductor, so it's probably not all of the answer. We might need some accessory minerals that are also conductive. So in South Australia, I know they've invoked fluorine as a conductive thing. And my understanding is there is fluorine up here somewhere. So tell me if I'm wrong, but that's another possibility. But for something this strong, it has to be graphite. It can't really be anything else.
There's lots of fluoride at Mount Margaret, isn't there?
Yeah. See, a little bit about geology.
So there's a million different questions I could ask, but I don't want to hog the mic. But I really enjoyed the talk.
Thank you.
One thing that really sort of strikes me about the MT processing is just the amount of computer grunt that you need to get it done. Is there a light, on the horizon where that processing could happen more quickly? Is it something that as our capability gets greater and greater, both in software and hardware, that we'll be able to process the MT?
Yeah. So
quickly?
My hope is Yes. So some of the limitation in running an inversion of MT is the maths, like the calculation of electrical structure in a forward sense is what is chewing all of the compute time in these inversions. The inversion is relatively quick. And so that fundamental maths doesn't change. Whether or not we need an absolute solution to that or an approximation for that is a question for people who know a lot more about maths than me. But I know there's work going on in that space about what do we actually need to generate an inversion that's coherent and what shortcuts can we take through the maths to get there in a way that is a lot quicker. So, I mean, raw increases in compute power, obviously going to help. Different inversion codes might be better optimized. So at the moment, a lot of this work relies on one code. There's not that many 3D inversion codes out there. The one I'm using is available to researchers freely by one of the community members. There are commercial implementations, but try running as many models as I did on a commercial implementation and you end up with quite a large bill. So yeah, so I think there is work being done. I don't think it'll be quick enough to satisfy anyone. But hopefully soon there'll be some advances in that space.
Yeah, quantum computing.
No.
Even quantum computing won't help. Oh, there you go. It shows my ignorance.
Yeah, so recent times, so the comment that was made there was quantum computing, forget it, forward modelling isn't going to get sped up by quantum computing. Quantum computing solves a different class of problems, which is kind of sad, but there are other options. And one of those that's become quite popular in physics in the last few years is actually to train AIs to approximate the solution of partial differential equations. So you start by creating a training data set with actual forward models, which is a really compute intensive task. And then you train an AI to approximate that. And then you can slightly change the input conditions and boundary conditions, and it does a reasonable job of approximating the real solution outside of the bounds of the data set that you've started with. You're getting an 1,000 to 10,000 times speed up by doing that. But it is an approximation on top of an approximation.
Yeah. And so maybe you end up in a situation where you use that to test model space, but you need a foundation in genuine normal inversion.
Interesting discussion. Thanks, Janelle, again. Two questions, but they're kind of related. One of them was a lot of the data that you were showing distributed on your maps. I noticed it didn't include all the industry data that's getting produced and generated. One question is, do you have a plan to begin to integrate that in and model that as well, like the Anglo-American data?
Yeah.
And then kind of related to that, on your when I was at Anglo, we used NT a lot to constrain depth of basement.
Mm-hmm.
I really liked the method you outlined, but I was intrigued as to why you would bother using 1D rather than using 3D to begin with. Like, use the 3D to begin with, then go to because with 1D you can get lots of artifacts. That's my understanding. I'm not a aficionado.
Okay, so I'll answer the 1D one first because I like that one. I will answer the other one too, I promise. So 1D inversion is a hell of a lot quicker and you can make it a lot more fine. So if you were to do a 3D inversion of these sites, you have to make compromises on your model mesh, and then your ability to resolve exactly where the basement is different, is more defined by your mesh than reality. And then put on top of that, you can't 3D probabilistic model. It's not something we can do. There's no code that exists really. There's like one that's come out of Macquarie that might be a candidate, but we don't have a 3D probabilistic inversion code. So the parts of the data that have been modeled, and you're absolutely right, if you use 1D code to model data inappropriately, artifacts everywhere. But some of this data is truly 1D and only needs 1D inversion. So it adheres to all the assumptions of one-dimensional data. So the two phases of the data are plot on top of each other. And then when this data becomes not one-dimensional anymore, the neat thing about the code that Joel has generated is the error bars blow out, so that we are no longer forcing this code to match the data inappropriately where it shouldn't be doing it. So it only models the piece of data that's appropriate for it to model, which is the basins, conveniently. The basins are one-dimensional generally in MT. The question about the MT data from industry is a good one. There are not that many industry data sets that are going to be used in the scale of modelling that I generally do. The Anglo data set is an exception. I tried to get my hands on it and model it while it was confidential, and that wasn't taken well by Anglo, if I'm completely frank. But most exploration data is not at a scale that I can use in my modelling. I could downsample it to a point where I can use it in my modelling. A lot of it is not collected to a long enough period. In exploration, they don't care about doing an overnight read or 2-night reads. They collect what the contractor tells them to collect, and it might only be 8 hours, it might only be 16 hours. It's generally not enough to get you that deeper data that you need for this scale of modelling. And then it's also confidential for 5 years. So I haven't used any of it because most of it is still confidential, and what isn't confidential, it's not really at a scale I can use. After the 5 years, maybe. Yeah, maybe. But I will have all of my own sexy new data going in, which is much better than someone else's secondhand data. And exploration surveys are designed to find exploration targets. They're not going to answer these big crustal scale questions. Again, maybe with the exception of Anglo data. That's a very large scale data set that I will be getting my hands on when it's available.
So something industry could do, something industry could help would be to give you permission to use an R.
Yeah, sure.
So yes, for the industry folks online, something that you could do to help this process would be to give early access to this data, as Steve just pointed out. We have a question online from my old friend Emmanuel Wembenyui. Thank you, Janelle, for a wonderful presentation. Do you collaborate with other geological surveys, for example, the NTGS, such that data from the Mount Isa area can be integrated with data from the MT to see the extent of these conductive features you've identified? The Georgina Basin, just west of Mount Isa, has very limited or no outcropping rocks, and MT data will be extremely useful here, thus the need for cross-border collaboration.
Yeah, so I can tell you the Northern Territory Geological Survey is not collecting their own MT data. Their focus is somewhere else. Certainly we do collaborate through Geoscience Australia with the other surveys. Like, we are quite closely linked to the other surveys. We catch up quite frequently. We've done cross-border collaborations before. So we collected a big MT program in the Southern Thompson along the New South Wales border a couple of years ago, more than a couple of years ago. So it is something we absolutely do. It's not something that is a focus in the area that was mentioned for us at the moment. But it doesn't mean it won't be in the future, right? That's just not where we are.
Excellent. Thank you very much. Well, that's all we have time for this morning. If you please join me again in thanking Janelle for her presentation. Coming up next week, we're moving from the macro down to the micro and returning to the world of minerals processing. Our very own Dr. Susanna Brito-Yabriou from the JKMRC will be presenting her work on advanced surface characterization and posing the question, is this the next frontier in minerals research? I hope you can all join us again next week for that talk. Thank you very much.